Today we're going to talk about A/B testing and more advanced techniques in the AdTech industry. This is our agenda for today. Before agenda, a little bit about me. I used to work until January in Yahoo, not in the same group as Ira, but in the same field. Now I lead the data science team at Beta-Bid, a real-time bidding agency, where we can say that in Beta-Bid and Yahoo I have approximately 5 years of experience in the AdTech industry. Before that, I used to work for AT&T as a data scientist and at Microsoft as Kinect software developer. It was a long time ago. Okay, so this is our agenda for today. We're going to talk about what is A/B testing, what A/B testing is not, how can you solve other problems with different experiment design, such as factorial design. We are going to talk about what I think is the most major issue when handling with A/B testing, which is the convergence rate. Then we're going to talk about real-time A/B testing as CI/CD that was mentioned in the first lecture. Talk about deployment, about some hacks, how to make A/B testing converge faster, the coin-flip relaxation. And then we'll finish with I think the most complicated thing here is the Bayesian CPC, cost per click model. Okay, so I think this is the textbook example of an A/B testing experiment. We have an ad. It can be either circular or rectangular. And we want to know which version works better. Now, A/B testing, the A/B testing experiment is meant to control for only one feature. That's why it's red over there. The basic experiment design looks something like that. First, we split the data into two identical buckets. Now, it's worth mentioning that splitting the data is not as trivial as you might think. For example, let's say that a certain company, Yahoo, has a server in the East Coast and in the West Coast. What could be easier than installing different software in each server? Well, it won't work, because maybe the audience on the east side, on New York, love different ads than the guys back in California. So we don't want to introduce any additional features when splitting the data. The most easy way is to split by user ID or timestamp or something like that. Okay. So after we splitted our data into two identical buckets, each bucket, this will be bucket A from now on, will get one version of the ad. And then we'll run it for a while. After a while, we can calculate and say, what is the average revenue for each bucket? For example, for the rectangular ad, we got $4 on average. And for the circular ad, we got $3. But maybe it's a coincidence, maybe we didn't have enough data. So this is where the statistical part of the A/B testing experiment design comes into play. The central limit theorem. I guess that most of you heard about this concept in like the first probability class that you took in the university. What the central limit theorem states is that eventually, when you have enough data, and you average enough observations, then again, eventually it's red, note that, the distribution is going to look like a Gaussian. So this is like the textbook example you see. First we average 2 numbers, then 3, and it looks more and more like a Gaussian. Okay, so once we agreed that we have a Gaussian distribution for bucket A and for bucket B, the difference of two Gaussians is also a Gaussian, basic probability. And applying the z-test is a way to measure, so it's a Gaussian and it's supposed to be centered around 0, because if the two buckets are the same, we would expect them to have the same revenue. So the further away the difference is from 0, the more likely it is that they are different. That's z-test in a nutshell. I guess that probably at least a few of you heard about the p-value concept. P-value is actually 1 minus the value of the CDF here. And this is a good point to stop and rant about the p-value. I think that there's no other concept that is more poorly misunderstood than the p-value. So p-value is not the chance of getting $1 more, as many people interpret it to be. And actually, it does not account for the effect size. It could be 1 cent, it could be $10. P-value doesn't care. What p-value actually is the chance of getting the same results if I were to run an AA test, meaning showing the rectangular ad twice. What are the chances of getting the same difference? That's it. So it's kind of backward from what most people understand, but that's the formal definition. Okay, so the first problem we have with the A/B testing experiment design. What if we have more than one feature? We can control for the shape and the color. What then? So the most trivial thing to do is to run A/B testing twice. First, we'll run it on the shape, for example, and then maybe we'll improve from this rectangular green ad to this circular green ad. And then second time, and we'll get to this optimal design. But what if our results look something like this? We'll never find out that this is the best design. Okay, so same results, but we have interactions over here. In other words, maybe people really dislike rectangular black ads, green ads for some reason, but those are ideal. The way to work around that is to have a different experimental design, which is called the factorial design, meaning that we're splitting not into 2 buckets, but into 4 buckets. So we have 1 bucket for each combination. As you can see, it can grow pretty rapidly into a lot of buckets, and our data will be very sparse eventually. So if you have like 10 different colors, 10 different shapes, and you want to control also for the text, you're going to run out of data eventually. So this is where convergence comes into be even a more serious problem. Okay, convergence. So we stated that the central limit theorem states that eventually the data is going to be a Gaussian, and this is a nice demonstration in Python. As you can see, for when we're averaging 2 numbers, then it looks some sort of triangular. 7 numbers, it looks pretty good. And for 30, which is like the magical number in statistics, you have to have at least 30 people in your sample, it looks tied on. So this is for the uniform distribution. But what if our basic distribution is skewed? For example, this exponential distribution. So here I'm starting from 30 observation, and you can see it's nowhere near a Gaussian. The orange line is the Gaussian approximation. For 300, it also doesn't look quite there, and even for 1,000, it has a lot of way to go. So eventually, it will look like a Gaussian. We can say that for sure, but it might take a while. Okay, so this is a talk about A/B testing in the AdTech industry. So this is how we make money at the AdTech industry. We have 3 types of campaigns. CPM is cost per mil, meaning that you get paid when someone sees your ads. It's usually good for companies like Coca-Cola, who released a new type of drink and want everybody to know about it. The next campaign is cost per click, which is by far the most popular, in which the advertiser gets paid only when a user clicks on the ad. This is what Facebook, Google, Yahoo, almost everyone is doing. And the last one is the CPA, cost per action. Action is usually an app install or a deposit in an app, or maybe buying in the seller's website. Those are really expensive. Like if you want to sell some kind of product for $100, you're going to pay at least $30 for a CPA campaign, and it makes sense because it's really hard to target those kind of customers. we'll focus on the CPC campaigns. So when you develop a CPC model, this is how your scenario looks like. You have a user. We are developing this wonderful robot. And we have a stock of ads that we can offer to the user. We get paid only if the user clicks. So our model gets the user features. For example, it's a female, I don't know, age 20 to 30. We need to find what is the best match for that profile. We serve her that ad, and we hope she will click. If she does, we get paid. If she doesn't, tough luck, but this is the majority of the cases. And as you can guess, 99% of the users don't click on the ads that they see. So now the A/B testing experiment looks something like this. We have two versions of our model, and we want to know which one performs better, this yellow bot or this blue bot. And the question is, when should I stop? When can I stop performing the experiment and start making some real money? And it's not that obvious. For example, here I got a click-through rate of 1%, meaning 1 out of 100 people clicked the ad, and I earned only $100. And here I earned a little bit more, but a lower CTR. So the decision is not always obvious. Maybe we need more data. And in practice, when you work on the development team, you keep on adding new features, and you want to know you're developing in the right direction. So here we added this kind of antenna. It's cool. The revenue is going up. Then we added this sword, and boom, revenue dropped. Is it a bug? Maybe just, this was during the Super Bowl, and now the Super Bowl is over, and we're back to normal. So we don't know. This is why we need to do an A/B testing experiment. OK, so we mentioned that the longer we run the experiment, the more money we lose, because we are not serving the most optimal version of the ad. And we want to combat this issue. A way we find out, which is pretty simple, is to separate the time into several independent intervals, for example, between 12 to 1, 1 to 2, and so on. Run those two versions of the model and see who is the winner. OK, for example, here the winner was the green bot, the yellow bot, blue. And then count how many wins and losses each bot has. Then we'll not use the z-test, which relies on the normal distribution. We will use a coin flip experiment, meaning a Bernoulli distribution. And we want the number of wins and losses to be approximately the same. OK, so we simplify the model a bit, and convergence runs a little bit better. But can we do better? Now, this is the part that's a little bit more hardcore on the math, so please feel free to stop me if you have any questions. I think that the best time to ask questions is when you have them. Using Bayesian statistics is a framework for us to use more prior knowledge with less data. So we need to bring some of our own data on how the revenue is constructed, and then we can get to conclusions faster. So we get paid, the revenue that we look at, we get paid only if there was a click. So we have the CTR, the percentage, the chance of getting a click, and the CPC, meaning the cost that the advertiser is willing to pay after he won the auction. So when you go to see a website, there's an auction behind the scenes, and every advertiser bids some amount of money. For example, if I would like to advertise, I don't know, razor blades, and I see that a male enters the website, I would bid more than a woman, for example. So every advertiser places its bids, and then we get our CPC, our cost per click. We saw that the coin flip abstraction is a pretty good approximation for the CTR. But what about the CPC? So we did what every good data scientist does, and we plotted the data. And the blue dots are the actual bids that advertisers are willing to pay on average. So, as you might guess, most advertisers don't want to pay a lot. And there are a few exceptional advertisers that need to pay $1 and above. If we approximate this kind of distribution with an exponential decay, which you can see it's not the best match, but it looks pretty close, then we can apply Bayesian statistics to this distribution. Now, in general, after we decided that our likelihood distribution is an exponential distribution, we need now to define what is the decay rate. Generally, we can choose any kind of prior distribution on the decay rate. This is how we use PyMC to define the belief distribution to be normal, meaning that I think the decay rate is going to be somewhere between this lambda and with this standard deviation. But running a simulation is costly. It might take some time. And as long as we're choosing the distributions, why not choose the easy one? So if we choose a conjugate distribution, now for those who never heard about Bayesian statistics, a conjugate distribution means that we have a closed form formula. So it's just a formula that we can substitute in, and we don't need to run any simulations or to. It's cheaper, basically, and easier. So if we accept that we use the gamma exponential, meaning that we know that the likelihood is exponential and the decay rate is gamma distributed, then we can use this wonderful package written by me that actually implements a table from Wikipedia of conjugate priors. It's like a 3-liner, and you have this wonderful plot. Okay, so this is how Bayesian coin flip experiments look like. In a coin flip experiment, we want to know what is the coin probability. If it's fair, then it's 50%. We start with an uninformative prior. We have no idea where is the p-value, what is the probability of the coin. It could be anywhere. Then we toss it for 20 times, and we got 9 heads and 11 tails. Now we're pretty certain it's somewhere here. It could be between 0.2 and 0.8. And after we toss the coin again and again, our belief becomes narrower. Now we're pretty sure that it's between 0.8 and 0.52. So if we're going to toss it for an infinite amount of time, you're going to get only the 0.5 distribution. So it's a different way to think about this experiment. How do we apply this kind of logic for the A/B testing experiment? We derive our prior from bucket A. So from bucket A, we can say that we're pretty sure our CTR is going to be somewhere here, between 0.1, I think, in this example. And then we update our beliefs with bucket B. And then, as you can imagine, the whole distribution shifts for a bit. What this gives us is a very nice probability value, which is not the p-value, by the way, which gives us the actual probability of those two buckets being the same. So we need to define what is our acceptable error margin. Here it's 0.1%. And then we can calculate the credible interval. All of this is done by the conjugate prior package. You don't need to write any code, except this line. And we get that the probability of those two buckets being the same is 1%. Okay, so we wrote like 3 lines of code, and we have an actual probability of those two buckets being the same. Assuming the priors. That's a good disclaimer to say. Okay, so things to consider when applying Bayesian statistics. First, you need to understand your model. That's it. So understand your model. Bayesian statistics requires domain knowledge. Priors, choose them carefully. If I were to choose different priors, I would get different results. We had some assumptions. For example, we assumed that the bids looks exponential. If these assumptions cease to be true, then this whole model fails to be accurate. So make sure that your assumptions hold. And conjugate trials are a useful hack, but sometimes you need to actually run simulations for these. If you need to run actual simulations, then use MCMC techniques like PyMC3, PyStan. There's a lot of packages, but still, those are pretty useful techniques. OK, so to summarize, we saw an A/B testing experiment. We saw Factorial. Factorial experiment. We saw how A/B testing can be used when deploying models in production. We saw a relaxed version with a coin flip and a more advanced version with a Bayesian CPC model. And I got the chance to promote the conjugate prior model.
So curious about when to choose the Bayesian instead of the frequent method, and always around, like, is there, like, depending on the data, the size?
So I don't know how to answer this question without starting a war, because there's because Bayesian and frequentists have answers to this question. Let's just say that if you don't have a lot of data and you want to convey your priors intelligently as possible, then Bayesian is the way to go. And if you don't, there are things that are easier to do for the frequentist with the frequentist techniques. For example, hypothesis testing. So use both of these tools, but by far Bayesian tools are far less familiar to the audience. Any other questions?
Confidence level?
So the question was, how do we know with the Bayesian method that it didn't stop too soon? And actually, I don't have an answer for this method. We tried to run it for a while, and some of the time we were right, and some of the time we were wrong. It's an approximation. Eventually, in this context, you have a cost of running an experiment. So we want to make sure that overall, your experiment is not very expensive. I hope that answers your questions, kind of. Thank you.